In this video, we will discuss about Inception Network and a very specific kind of Inception Network called as Google Net. The Inception Network first was proposed in 2015 in a paper titled Going Deeper with Convolution. Later, a very specific model for Inception Network called as Google Net was built, which later went on to have one of the top results in the 2014 ImageNet competition. So the key idea behind Inception Network is to have parallel convolution layer, as you can see in this figure. So here we have a parallel convolution layer, a 1 cross 1 convolution, another convolution with a kernel size of 3 cross 3, another convolution with a kernel size of 5 cross 5, and even a max pooling with a window size of 3 cross 3. And finally, the results are concatenated. Now, there was a really inspiring motivation behind why people even thought about an Inception network. For instance, in this slide, you can see 3 images of dog. But as you can see, the area occupied by the dog in each of these images are very different. In this image, the dog almost occupies the entire image, whereas in the second image, second photo, the dog is almost to the center of the image, whereas in the third image, the dog is just using a very small portion of that total image. So because we can have such huge variation in the location of the information, choosing the right size kernel for the convolution operation actually becomes very tough. So if you remember, while we were coding the convolutional layer, we have to give the size of the filter. The size of the filter we will use for performing the convolution operation. And we can give filter size of 1 cross 1, or it can be 3 cross 3, it can be 5 cross 5, it can be 7 cross 7. So it is actually a very tough choice to decide between which kernel size or filter size to use. And the choice of this filter size is very important in order to capture the information or the object present in our image. For example, a larger kernel is preferred for information that is distributed more globally. For example, in our first image where the information is distributed, so you have the information of the dog almost fully covering the entire image. So for such images like the first photo, we would prefer a kernel of larger size, that is probably a 5 cross 5 kernel or a 7 cross 7 kernel to capture this information, all the information present in our first figure. Whereas we use a smaller kernel for information that is distributed more locally. For example, if you take the third image where the information of the dog is very small, it's very restricted to only a small portion of that image. So in that case, we would prefer a smaller kernel, which is like a 3x3 kernel. So it is always very challenging as a designer of a CNN to actually choose the correct filter size. And moreover, most of the time the data set that we will have all the three types of these images, right? Where the information is like very much spread across the entire image. Or the last case, wherein last example in this slide, like where we have information which is very restricted to only one portion of our photo, or which is like in this second image where it is almost like within the middle, right? So you can have all these images in your data set, and so it is not efficient to rely on just one kernel size. And this is where this concept of Inception module comes into play, wherein which we are not in the pressure of deciding which convolution to use, in the size, which kernel, in the sense which kernel size or which filter size to be used, but rather we have the freedom to use all the filter size that we wanted to try out and later concatenate the result. So let us see how this is actually done. So as I mentioned, while designing a convolutional layer, we have to decide whether to have a convolution operation. If to have a convolution operation, which kernel size I have to choose, whether to go with a 1x1 or a 3x3 or a 5x5 kernel size, or do I just have to perform a pooling operation in that convolution layer? So what the Inception module does is, it says, let us do all these things and finally concatenate our result. But of course, this will make our network architecture very complicated. But we can always rely on that this network will always work remarkably well. For example, if I have say a 28x28 image which has a depth of say 192. So what the Inception network say is, instead of choosing which filter size you want in your convolution layer, or do we actually need a convolution layer, or do we just have to perform a pooling operation there? So instead of brainstorming over these questions, let us do all of these and finally concatenate our result. So let us start by first doing a 1x1 convolution. So, and let us say that the number of filters I will be using is equal to 64, and the 1x1 convolution, so it automatically means that my 1x1 convolution will have a depth of 192, which is the same as that of my number of channels in my input. So the resultant of this would be, of course, n minus f plus 1, which is 28 minus the size of the filter, which is 1, plus 1, which is equal to 28. So this gives me again a 28 cross 28 image, but the depth of my image will be always the number of filters, which in this case is 64. So it gives me a 28 cross 28 cross 64 output. Now, suppose that I also wanted to try a 3 cross 3 convolution, and since I wanted to have the NH and NW of my output same as the NH and NW of my input, which is 28, 28, I need to use a padding is equal to same. So that means P will be equal to F minus 1 by 2, and my F, size of my filter, is 3. So 3 minus 1 by 2, which is 2 by 2, which is 1. So I have to have a padding of 1 for my output to have the same height and width as that of my input, which is 28 and 28. And suppose I am using the number of filter to be, say, 128. And of course the 3 cross 3 filter size means 3 cross 3 cross the depth would be the same as that of the depth of the image, which of the input, which is 192. So when I do this, the output would be N plus 2P minus F by S plus 1, which is equal to the N, size of the image is 28, plus 2 into paddings is 1, minus the filter size is 3, divided by a stride of 1. So I will take the stride to be 1, and plus 1. So this will give us an output of 28 plus 2 minus 3 by 1 plus 1, which is nothing but equal to 28. So this result in again a 28 cross 28 image, but with now a depth of 128, which is I get from the number of filters I have used, which is 128. Now similarly, I say that now I will do say 5 cross 5 convolution. So I have now a 5 cross 5 convolution, and of course its depth will be 192. Again, padding is equal to same, and say I will use the number of filter to be 32 and stride to be equal to 1. So since I have used a padding is equal to same, that means I will have the NH and NW the same as that of my input. So I will have again a 28 cross 28 image, but with now a channel of 32, because that is what my number of filter is. Now again, say I wanted to also use I also wanted to use, say, max pooling. So max pooling, and for that, since I have to make the output same as that of the input, I definitely have to do a padding for pooling operation. So usually in our convolutional layers, we use padding in order to reduce dimensionality. So we don't technically add padding normally in our pooling operation, but in this case, since I wanted to finally concatenate all of my result, I need the NH and NW to be the same as my input. So I have to do a padding here, which again will be, I will be using the same padding. And here I will use a filter size or a window size of 3 cross 3. And of course 3 cross 3 means 3 cross 3 cross 192. And I will use a stride of 1. So that means my output would be n plus 2p minus f by s plus 1. So my padding p will be f minus 1 by 2, where f is the size of my filter, which is 3, minus 1 by 2, which is equal to 2 by 2 equal to 1. So that is equal to n is 28 plus 2 into 1 minus the filter size is 3 divided by stride is 1 plus 1. So that is equal to 28 plus 2 minus 3 by 1 plus 1, which is equal to 28. That means I get a resultant of again 28 cross 28, and my channel will be the same as the size of my input. In the case of pooling operation, the channel of my output would be the same as the channel of my input, which is 192. So what I can now do is I will combine all what we have done. So here I have done a convolution operation, a 1 cross 1 convolution, a 3 cross 3 convolution, a 5 cross 5 convolution, and I have also done a max pooling. So the whole idea of having an inception module, for example, in this case, is that I have an image of 28 cross 28 cross 192, and this result me an output of 28 cross 28 cross, when I add these values 192, 32, 128 plus 40 plus 64, I get 416. So it outputs me a image or object of 28 cross 28 cross 416. So the whole idea behind the Inception module is that as a designer or as an architect of a CNN, you don't have to decide what should be my filter size, or do I actually need a convolution operation there, or do I just need a max pooling operation there. So you don't have to commit to anything. What you can do is you can do all these things in the Inception module, and then just concatenate all the outputs and let the network learn for itself whatever parameters it want to use or whatever combination of these filter sizes it wants. But obviously, after doing this example, you might clearly see one problem of inception layer, which is, of course, computational cost. So, even though this architecture will perform very well than a traditional convolutional neural network architecture, it has this drawback of high computational cost. So let us see what the computational cost would be roughly for this particular architecture. For that, what I will do is I will not do all these four computation. I will not find out all the computational cost for all these four operations. So let me just pick one of these. Say I will pick 5 cross 5 and I will see what its computational cost is. Then you could marginally guess what the computational would be for 1 cross 1, 3 cross 3 and for max pooling. And if you sum up what value of computations cost you will get. So let us just take our 28 cross 192 input and just look at the 5 cross 5 convolution. So it is 5 cross 5 cross obviously 192, and I had used a padding is equal to same, and I have used in my example the number of filters is equal to 32. And this gave me an output of 28 cross 28 cross 32. So let us just roughly calculate what the computational cost of just one operation of this would be. That is just for 5 cross 5 filter, and then we can imagine how high would be the cost for others, and when we sum up how will be the computational cost in total. So here, as you can see, the output size is 28 cross 28 cross 32. That means we need 28 cross 28 cross 32 numbers, and for each of that we need to do 5 cross 192 multiplies. That means in total I will need the number of multiplication operation for just this one will be 28 into 28 into 32 into 5 into 5 into 192. So that would be approximately 120 million multiplication operation. So remember, we are not talking about the number of parameters here, but we are talking about the computational cost. And how we determine a computational cost is by deciding how much arithmetical operations has to be performed during that computation. And in our case, the main arithmetic operation that we are interested is the multiplication operation. And as we know, multiplication operation is a very complex, a computationally intensive and computationally expensive operation, right, within a computer. So we are just looking into the multiplication operation here. So as you can see, in order to just perform this operation, we require 120 million multiplication operation. Now, even though today's computers are very equipped to have this 120 multiplication operation, it's still a very expensive computation. So we have this is just for the 5 cross 5 convolution operation. So it would be almost the same value for 1 cross 1, 3 cross 3, and for max pooling. So we have to think about a way wherein which we can decrease this computational expense. Now this is where our 1 cross 1 convolution that we have discussed in our previous lecture will come handy. So again we will take our 28 cross 28 cross 192 input image, and before performing our 5 cross 5 convolution operation, what I will do is perform a 1 cross 1 convolution. So that means, of course, 1 cross 192, right? And the number of filters I will be using is 16. So in that case, what happens is the output would be obviously 28 cross 28 cross 16. So as you can see, the depth of my channel decreases. So my whole idea is to have this same input 28 cross 28 cross 192 and get an output of 28 cross 28 cross 32, right? My input and the output should be the same what you see in this example. So as I have said, I first do a 1 cross 1 convolution operation with a filter size of 16, which gives me now an output of 28 cross 28 cross 16. So obviously it is from the formula n minus f plus 1. N is 28, f is 1 plus 1. So I get 28 cross 28 cross 16 comes from the number of filters. Now after this, what I do is now perform a 5 cross 5 convolution, and the number of filters I will use is 32, right? And the padding will be, I will be using the same padding, and I will use a stride of 1. So this will give me an output of n plus 2p minus f by s plus 1, which is equal to, now my n is 28 plus 2 into padding. So p will be, since I have used same padding, p will be equal to f minus 1 by 2, which is where f is the filter size, that is 5 minus 1 by 2, that is equal to 4 divided by 2 equal to 2. So that would be 28 plus 2 into 2 minus f, the size of the filter is 5, divided by stride of 1 plus 1. So that would be equal to 28 plus 4 minus 5 by 1 plus 1, which is equal to 28 minus 1 by 1 plus 1, which is equal to 27 by 1 plus 1, which is of course 28. So you get an output to be again 28 cross 28, but the depth will be now equal to my size of the filter, which is 32. So as you can see, my input was 28 cross 28 cross 192, and I have now got an output of 28 cross 28 cross 32. So this was the same which I have in this example while I was computing the computational cost, but here I have applied a 5 cross 5 convolution directly to my input to get an output of 28 cross 28 cross 32. But in this example, I have first used my input, convolved it with a 1 cross 1 convolution operation, and then convolved its result with a 5 cross 5 convolution operation to get the same output as the previous example, which is the 28 cross 28 cross 32. Now let us go ahead and calculate what will be the computational cost for this entire process. So as you can see, I have my 28 cross 28 cross 192 image, which is first convolved with a 1 cross 1 convolution operation to get an image of 28 cross 28 cross 16, and that is now convolved with a 5 cross 5 filter to give me an output of 28 cross 28 cross 32. So I have my input and I have my output, which is the same as this example here, which I used to show the computational cost. But the only difference is that in this example, I have a 1 cross 1 filter here before applying a 5 cross 5 convolution. So let us now go ahead and calculate the computational cost for this example. So in this case, so for performing this computation, so you can see my output is 28 cross 28 cross 16, which means I have 28 cross 28 cross 16 numbers, and I need to compute 28 cross 28 cross 16 numbers, and for each of them I need to do 1 cross 192 multiplications. So that means, so when I multiply all these, I get approximately 2.4 million. And now let us look this particular operation. So for that, we need to compute again 28 cross 32 numbers, and for each of them we need to do 5 cross 32, sorry, 5 cross 5 cross 16, right? Because this is 5 cross 5 cross 16. So 5 cross 5 cross 16 multiplications. So this is, when multiplied, is equal to 10 million. So when I add these two, I get 12.4 million. So that means if I inserted a 1 cross 1 convolution operation at the middle, what happens is that my total computation cost will be only 12.4 million. That means I need to perform only 12.4 million multiplication operation for this particular case, whereas if I was to directly apply the 5 cross 5 cross filter onto the same image, I would have to use a 120 million multiplication. So clearly we can see that introducing this 1 cross 1 convolution operation in the middle has decreased our computational cost to nearly 1/10. So in summary, if you are building a layer in a convolutional neural network, we don't want to decide on which size kernel I should be using, or even to decide whether I need to do a convolution operation, or can I just do a pooling operation. So in that case, the Inception module comes very handy, because now I don't have to decide what my filter size is, but rather what I will do is I have the ability to perform a parallel computation with all of my filter sizes which I have in mind. But of course, we have seen that when we do that, the computational cost is very large. And in order to overcome that, we have used a 1 cross 1 convolution. So we use a 1 cross 1 convolution in the middle so that we can reduce the computational cost very significantly, but yet get the same model performance. So that is what is Inception module. So this slide correctly summarizes what we have done so far with Inception module. So this is how it all started, with the naive version, wherein which I was performing parallel computations with 1 cross 1 convolution, 3 cross 3, 5 cross 5, and max pooling, and finally concatenating that result. So as we have discussed in the Inception module, we don't have to worry what is the best kernel size or the best filter size, but we let our network decide for itself based on the image that it receives what is the best of the convolutional operation combinations that will work for them to extract the best information from those images. But as we discussed, these Inception modules, even though work very well and gives us good performance, its main problem was computational cost. So in order to prevent that, what we have done is we have introduced 1 cross 1 convolutions before all my operations. So as you can see, so in this case, I'm performing my 1 cross 1 convolution. Here I'm performing my 3 cross 3 convolution. But since these 3 cross 3 convolutions are very computationally expensive, what I have done is I have performed a 1 cross 1 convolution first before performing the 3 cross 3 convolution. Again, similarly, here you can see I have performed a 5 cross 5 convolution, but before performing a 5 cross 5 convolution, I performed a 1 cross 1 convolution, because otherwise this 5 cross 5 convolution directly on my input layer would be very computationally expensive. Similarly, I have performed a max pooling operation. So as we know, in a pooling operation, the size of our channel, that is NC, will be same as that of our previous layer or our input layer, right? So that means if my previous layer had say 128 depth or channel, the NC for the max pooling after the max pooling operation would also be 128. So technically we have discussed that max pooling does not reduce the depth of the image, but rather it only shrinks the height and width of your input image. So in order to decrease the depth of this image which we obtained through max pooling, what we do is perform a 1x1 convolution. So this will then be all concatenated to get our final output. So this is how a inception module works.